Hello everyone, welcome to my YouTube channel. Today I want to start a course on optical spectroscopy. In this course we need some background and some basic concepts from quantum mechanics. So for our first lecture I'm going to introduce a blackbody radiation problem. So quantum mechanics started by this problem and the solution which was proposed by Max Planck. So consider you have a box which is in the T temperature. So this empty box has a hole which our detector could be in front of it and we can detect the radiation comes out from this box. So we have this electromagnetic wave inside the box because of this temperature. When we increase the temperature to T, for example, the molecules and atoms of the shell of this box started to vibrate and emit light. And here we consider that our box is black. Black, it means that absorbs all wavelength, all electromagnetic waves in different frequencies, and in response every of these electromagnetic waves which absorbed by the shell of this box again vibrate in other molecules and atoms, and we have the emission of another electromagnetic waves. So this absorption and emission are in equilibrium. So here we want to calculate the total energy of electromagnetic wave in range of omega to omega plus d omega in this range. Consider the volume of our box is L cubed. So the length of in each direction is L and the volume would be L cubed. And the energy density of this electromagnetic wave inside this box would be the energy of electromagnetic waves over the volume. So in order to find the total energy, we need to multiply to the volume in order to find the total energy. So basically, as I said, this total energy should be proportional to the temperature. So in this box, we have empty space and we only have electromagnetic waves. From the classical physics, we know that we have to solve Maxwell equations for this empty box. So we can write the Maxwell equations for electric fields and magnetic fields. And of course, we don't have any flux or any source of current or source of charge. If we mix these two equations, we can get the electromagnetic wave equation, which is a very famous one, and we already know that this equation, which is known as electromagnetic wave equation, has a very common solution, like a plane wave times a time-dependent function. So it could be a linear, of course, a linear combination of these terms. And when you insert this solution, this guess, into this equation, you will get an equation looks like the harmonic oscillator equation, which here I show it by 2 star. So this is really similar to the harmonic oscillator equation. So when I put this into the wave equation, I get this equation, and from this I will get harmonic oscillator equation. And we know that omega is equivalent to ck. C is the velocity of the propagation of light in this box, which is known as light velocity. So if we consider our box made of metal, we have the boundary conditions, and we can apply these boundary conditions and find these modes or the frequencies. So if the box is made of metal, the electric field around this box would be 0. Therefore, we have in the 6 faces of this box, this cubic box would be 0, and we apply this for different position of x, y, and z, and we will get from this condition we will get the wave numbers in different directions, which is proportional to pi over the length of each direction. So if we visualize this in the k space, the valid k points would be proportional to pi over L. And our valid k points are discrete somehow. And as you know from statistical mechanics, we can write the average energy for harmonic oscillator where these equations, so this is the average energy of harmonic oscillators, which is proportional to the square terms of each. And from the equipartition principle in statistical mechanics, we know that every square terms has 1/2 kBt energy, thermal energy. So we have 2 terms, therefore we have kBt. So if you don't remember this from statistical mechanics, you can simply solve the mean energy by solving this integral. So we have a Gaussian integral here, and we just, so here we have the energy, so the mean value would be the energy times the distribution of energy, and then we also should have normalized that. And we get kT if you solve this. Well, now we want to see what is the energy between omega and omega plus d omega. So in order to do that, we have to find what is the number of modes in the shell from omega to omega plus d omega, or you can translate it by this relation to the k. So from k to k plus dk. And the number of points here, we show it by dn, right? So in order to find the energy, we must find the volume, which consists of 1 point. So the volume of 1 point would be such a volume, right? So in 3 dimension, we have pi over L, so pi over L cubed. So the energy in the volume from K to K plus dk would be this volume, this number per volume, times kT as we measure here. And Kb is the Boltzmann constant. So this dN would be the volume of this shell that we showed here, right? Which is 4 pi k squared dk, and over, because we have density here, over the volume of 1 point. But there is a problem here, because if we do this, we have the number in all phase space, and we just need a positive k points, because our n1, n2, and 3 are positive. So we have to multiply to the 1/8 this volume. So we multiply this to 1/8, we have kBt times dN. And also, we have two directions for electric field, which are perpendicular to the propagation of light. And here we just assume a one direction, so we have to multiply to 2. So the polarization of E field can be also clockwise and anti-clockwise. So we have this 2 times 1/8 times this dN times kBt. And as previously we showed that we have to also times to the volume to find the total energy. So the total energy would be the integral over this u omega d omega from 0 to infinity. And if you can see here, the integral will not converge but diverge. And this is 100% unreal results. And because the energy in the box cannot be infinity, we have the problem here. So either the classical physics doesn't work, or we are missing something. So if we do the same things for magnetic field also, we will get the same result for the energy. So up to now we introduced the problem which they were facing in the classical physics. And so Planck proposed a hypothesis to solve this problem. Instead of using a kBt for each mode of the electric field, for example, he somehow assumed that our energy is discrete. So the energy corresponding to each mode is proportional to the omega, and this n is from 0, 1, 2, and there are real numbers. So h bar, which is a Planck constant, also is a constant just to correct the dimension. So in the left hand we have the energy, and in the right hand we have a frequency. So h bar somehow we have to put it to correct the dimension. So basically what he did was more mathematical efforts than adding some physics to the problem. So instead of playing with kBt, now we want to find the average energy for our case now here, which is n h bar omega. So if we do this calculation, we find the mean average. We reach to the function like this. And this summation somehow can be calculated. It's not really difficult. So it gives us this function here. So if we put this part instead of kBt, so now we don't use kBt, but we use this function instead, and we get such a function with these constants part. And this function exactly gives us the very well curve which fits to our experimental result. And this was an effort to reach the very well fit to the experimental result. So let's consider limits where the frequency are low, corresponding to with respect to the temperature. So in the low frequency, our function has the behavior of omega square d omega. So in this part, we have omega square shape. And for higher frequency, how about higher frequency? We have this behavior, which exactly fits with our function here. And it is very well known law, it's called Rayleigh-Jean's law. So up to now we didn't do the integration yet, but if you do the integration, your integral would be proportional to the 1, so like 1/2. So if you do the integration to find the total energy, your energy would be proportional to T4. And this is very famous law. It is called a Stefan-Boltzmann law. And of course, if you want to know where this peak appears, you have to take a derivative of this function and find this omega max. And this is also known as Wien's law. And it shows that there is a inverse proportionality between lambda, the wavelength, and the temperature. So as you increase the temperature, the peak goes lower and lower. And as you can see in this plot, as we increase the temperature, the wavelength corresponding to each temperature goes down. And this is the range of visible lights. So in the higher frequency, or let's say lower wavelength, we have ultraviolet, and in the mid range we have visible light, and in lower frequency or higher wavelength we have infrared. And that was the end of this session about the black body radiation problem.